everyone, welcome to the AlgoAI channel. Today we are learning about shell sorts, which is sorting algorithm used to arrange data in a specific order such as ascending or descending order. Shell sort is an in-place comparison-based sorting algorithm. It is an improved version of insertion sort. The main idea behind shell sort is that instead of comparing only adjacent elements, it allows the comparison and swapping of elements that are far apart. This helps reduce the number of shifts required to sort the data. Key features. One important advantage of shell sort is its efficiency. Compared to simple insertion sort, shell sort works much faster when dealing with large datasets. Another key feature is its gap-based approach. The algorithm starts by dividing the list using a large gap between elements. As the sorting process continues, the gap is gradually reduced. This method helps move elements closer to their correct position earlier in the process. Shell sort is also an in-place sorting algorithm, which means it doesn't require extra memory to store another array. This makes it memory efficient. Additionally, shell sort is adaptive. If the array is already partially sorted, the algorithm performs even better. The key idea of shell sort is that by first sorting elements that are far apart and then reducing the gap, step by step, elements move closer to their final positions, much faster than in insertion sort. Then let's talk about what is a gap. A gap is the distance between the elements we are comparing in the array. Unlike normal insertion sort, which only compares adjacent elements, shell sort first compares elements that are far apart. The algorithm does multiple passes over the array, and each pass the gap value decreases. This allows the elements to move closer to their final position quickly. Common gap sequence. There are several ways to choose the gap. The first one is shell's original sequence. This is simple and works well for many cases. The second one is Knuth sequence, a slightly more advantageous sequence that often improves performance. The third one is Sedgwick's sequence, more complex, but in practice it can perform even better for large arrays. Now, let's see exactly how shell sorts works with a small example. This will help you understand why the gap sequence is so powerful. We will take a simple array of 6 elements: 12, 34, 54, 2, 3, and 11. The first step is to calculate the initial gap, which is the array length divided by 2. Here, the length is 6, so the initial gap is 6 divided by 2, which equals 3. Step 1. Gap equals 3. With a gap of 3, we are compare elements that are 3 positions apart. This means compare index 0 and 3, 12 and 2. Since 12 is bigger than 2, we swap them. The array now looks like 2, 34, 54, 12, 3 and 11. Compare index 1 and 4. 34 and 3. 34 is bigger than 3, so we swap them. Now the array becomes 2, 3, 54, 12, 34 and 11. Compare index 2 and 5, which mean 54 and 11. 54 is bigger than 11, so we swap them. The array is now 2, 3, 11, 12, 34, 54. After this first pass, notice that the gaps are corrected first. Elements have moved closer to their final positions. Even true, the array is not completely sorted yet. This is why shell sort is faster than simple insertion sort on larger datasets. Step 2. Gap equals 1. Next, we reduce the gap to 1, which is the final pass. Now we perform a regular insertion sort on the nearly sort array. 2, 3, 11, 12, 34, 54. Compare 3 with 2, already in order, no change. Compare 11 with 3, already in order, no change. Compare 11 with 11, already on order, no change. Compare 34 with 12, already in order, no change. Compare 54 with 34, already in order, no change. Since the array is already mostly sorted after the first pass, this final insertion sort is very quick. Result is 2, 3, 11, 12, 34, 54. Completely sorted. Insertion sort on sublist. Now that we understand gaps, let's see how shell sort uses them to perform insertion sort on sublist. Shell sort works by performing insertion sort not on the entire array at once, but on elements that are paired apart by the current gap. This effectively creates virtual sublists within the array. By sorting these sublist, elements can move large distance early on, which speeds up the sorting process. Example with gap equals 3. Let's use the same array we saw earlier. 12, 34, 54, 2, 3 and 11. With the gap of 3, the array is divided into virtual sublist. Sublist 1, 12, 2. Elements at indices 0 and 3. Sublist 2, 34, 3. Elements at indices 1 and 4. Sublist 3, 54, 11. Elements at indices 2 and 5. Now, each sublist is sorted independently using insertion sort. In sublist 1, 12 and 2 are compared. Swap. Array becomes start with 2, end with 12. In sublist 2, 34 and 3 are compared. Swap. Array becomes start with 3 and end with 34. In sublist 3, 54 and 11 are compared. Swap. Array becomes start with 11 and end with 54. After sorting these sublists, the array becomes partially sorted. Elements are much closer to their final positions. Why this works? Elements jump over large distance, moving closer to their correct positions faster than insertion sort alone. The array becomes partially sorted quickly, which reduces the total number of comparisons later. In the final pass, when the gap is 1, we perform a regular sort on the nearly sorted array. Since insertion sort is fast on nearly sorted arrays, the final step completes the sorting very efficiently. The key takeaway is by performing insertion sort on these gap separated sublist, shell sort combines the speed of moving elements in large jumps with the accuracy on insertion sort, making it much faster than ordinary insertion sort, especially on large arrays. Now, Let's look at a step-by-step example to understand shell sort clearly. The initial array is 12, 34, 54, 2, 3 and 52. The size of the array is 6. So the initial gap is 6 divided by 2, which is 3. Then the next gap will be 1. In the next slide, I will explain how the sorting happens step by step. Breaking down the process. Here, step 1, gap equals 3. The first gap is calculated as n divided by 2. So 6 divided by 2 equals 3. With the gap of 3, we compare elements that are 3 positions apart and swap them if needed. Compare index 0, which means 12, with index 3, which means 2. 12 is larger than 2, so we swap them. Array become 2, 34, 54, 12, 3 and 52. Compare index 1, which means 34, with index 4, which means 3. 34 is larger than 3, so we swap them. Array become 2, 3, 54, 12, 34, 52. Compare 54 with 52. 54 is larger than 52, so we swap them. Array become 2, 3, 52, 12, 34, 54. After this pass, notice how large elements have moved closer to their correct positions, even though the array is not fully sorted yet. Step 2. Gap equals 1. Now we reduce the gap is 1. This is the final pass, which is this standard insertion sort on a nearly sorted array. Move 12 to its correct position. Compare 12 with the 52, move 12. Array becomes 2, 3, 12, 52, 34, 54. Move 34 to its correct position. Compare 34 with 52, move 34. Array become 2, 3, 12, 34, 52 and 54. And now the array is fully sorted. 2, 3, 12, 34, 52 and 54. This is the sorting array we talked about earlier. This means the array is now fully sorted. So, this animation clearly shows how shell sort improves efficiency by first sorting elements that are far apart and then finishing with insertion sort on a nearly sorted array. Shell sort was insertion sort. On here, we are comparing insertion sort and shell sort to understand why shell sort is faster. Let's start with insertion sort. Insertion sort always compares adjacent element, meaning elements that are next to each other. Because of this, the gap is always 1. It makes only one pass through the array. And when the element needs to move far, it moves step by step, one position at a time. This causes many small shifts, especially when the array is large and unsorted. So, insertion sort becomes slow on large unsorted arrays. Now, let's look at shell sort. Shell sort starts by comparing distant elements first, not just adjacent ones. Instead of using a single gap, it uses multiple decreases gap values. This means shell sort performs multiple passes, and in each pass the gap becomes smaller. At the beginning, elements move in the large jumps, which quickly reduces disorder in the array. Because of these larger jumps, shell sort needs fewer movements overall. That's why shell sort is much faster on large arrays compared to insertion sort. Now, let's look at the key advantages of shell sort. First, faster movements. Elements can jump across the array in fewer operations instead of moving one step at a time. Second, reduced inversion. Large gaps remove many out of order elements very quickly. Third, better performance. Shell sort works significantly faster on medium to large datasets. Finally, final pass efficiency. When the gap becomes 1, insertion sort runs on a nearly sorted array, which is its best case. So in summary, insertion sort is simple but slow for large data, while shell sort is smarter, faster and more efficient. Now, let's talk about why shell sort is faster using a simple movement example. First, look at the insertion sort approach. Imagine we want to move an element from position 5 to position 0. Insertion sort can move elements only one position at a time. So it requires 5 swaps. The element moves step by step from position 5 to 4, then 4 to 3, then 3 to 2, then 2 to 1, and finally 1 to 0. These many small movements make insertion sort slow, especially for large arrays. Now look at the shell sort approach. Shell sort uses larger gaps first. For example, gap 3 and then gap 1. With gap 3, the elements can jump directly from position 5 to position 2. Then, with gap 1, it moves from position 2 to position 0. So instead of 5 steps, shell sort needs only 2 or 3 operations. Because of these large jumps, elements found their correct positions much faster. Now, let's see the real-world impact. For an array with 1000 elements, insertion sort needs around 250,000 comparisons. Shell sort needs only about 10,000 to 30,000 comparisons. That means shell sort can be up to 10 times faster on average. So the main reason shell sort is faster is simple, fewer moves, larger jumps and smarter sorting. Now let's see algorithm implementations. This means n equal length of array determines how many elements are in the array. In this, shell sort started by comparing elements that are far apart. The initial gap is half the size of the array. In here, outer while loop keeps reducing the gap until it becomes 1. For I from the gap to n minus 1, iterate over elements starting from the current gap index. Prepares to insert array I into the correct position among elements gap apart. And this one temporarily stores the current elements. J equal I, J will move backward in the gapped subarray to find the right position to temp. in a while loop. This is gapped insertion sort. As long as the element's gap positions behind is bigger than temp, shift it forward. Move J backward by gap to continue comparing. In here, insert the element. Place temp in its correct position in the gapped subready. Reduce the gap. After one pass, the gap is halved. Smaller gaps mean elements are closer and the array gets more sorted with each pass. This one, return array. Return the sorted array. After the gap becomes 1 and the final insertion sort is done. The array is fully sorted. Now let's talk about key points. The first one is outer loop decreases the gap. Ensure that we start with far apart elements and gradually move to adjacent elements. The second one is inner loops perform gapped insertion sort. Compares and moves elements that are gapped apart, not just adjacent. The third one is final iteration. Gap equal 1. This is like a normal insertion sort. By now, the array is almost sorted, so this final pass is fast. The fourth one is in-place sorting. No extra array is needed. We have now come to the end. Thank you for watching. I hope this explanation of shell sort made it clear and simple. If you found this video helpful, like this video, subscribe my YouTube channel and turn on the bell icon. See you in the next video.